Swayam Prabha. Digital India. Educated India.
So, we have seen that there are plenty of sources of material data, and day by day the number of sources are also multiplying. In the sense, the body of material data is continuously expanding. In the olden days there was only experimental data, and people would get experience from experiments. And what is experience after all? Again, the data accumulated over a period of time and conclusions drawn from there, and so empirical laws or empirical relations were established in the olden days. So, these were established from a very restricted amount of data, very restricted sources of data. However, now in the modern times you have a large amount of data that is available from multiple sources. The ability to process that large body of data has also gone up due to computational power, and therefore extracting rules from this large quantity of data would naturally mean that the rules which you extract today might not exactly be the same as the rules which you had in vogue yesterday, and that is something which is which is some kind of progress. Now, the so called experience which is translated into data, basically digitalization of the experience is essentially what we call as data, that is materials informatics. So now the experience is documented in the form of different kinds of analytical theories. The data generated through different analytical theories, molecular dynamics and like continuum mechanics, FEM, and then finally through empirical equations as well. And then you have data pertaining to life cycle cost, life cycle assessment and life cycle engineering, so that environmental performance is achieved. So, basically now you are looking at the material selection or material behavior from not just the functional angle, but you are looking at it from multiple angles like cost, life cycle assessment and environmental performance of the material and many other viewpoints. So, basically the selection of the material becomes extremely complicated, in the sense that multifaceted, it becomes multifaceted, and a large number of conditions or constraints have to be satisfied by the material being used. You have standards and codes as sources of material data, but then these are kind of rigid. So, these are not like dynamic in nature. So, standards and codes are the ones which remain unchanged over a period of time, but then as you go on analyzing data coming from various sources, you might have to revisit the standards and codes and change them from time to time. So, this is how you have both static as well as dynamic sources of data coming in, and then we have an adaptive therefore an adaptive design approach that needs to be deployed. So, it integrates database that is built based on domain knowledge. So, domain knowledge is something which is well established facts. So, it integrates database that is built on domain knowledge and includes material data of targeted properties and descriptors, regressor, that is statistics based algorithms to regress targeted properties versus descriptors. So, basically what you do is that you would like to correlate the targeted properties with the descriptors, meaning control parameters. Basically descriptors would mean parameters which are under your control, which would influence the targeted properties to the maximum extent. So you would have a regression, or you would have a relationship between the two, and then you would have a statistics based algorithm to design new experiments or computations by optimizing the selection from exploration and exploitation of regions and feedback from experiments and computations. So what it means is that it is not just the correlation that is important, it is a tool which you use for correlation, whether it is a neural network or a regression based model or statistics based algorithm or model which is used. So whichever gives you the best accuracy of prediction has to be therefore utilized in order to correlate the two. So you have targeted properties and the descriptors, and these are correlated through experiments or I mean experimental data, computational data generated, and you select these the optimal tool which will give you the best possible predictions. So adaptive design takes feedback from new experiment and computation recommended by the best performing regressor, that regressor selector combination. So you have a regressor selector means the ML type of algorithm, and regressor would mean that there is a regression relationship between the so you select the best combination using a selector which is machine learning based, and then you put it into a regression model in order to get the prediction. So that is the best. So this selector combination, this regressor selector combination therefore gives you the best ML prediction. The new experiment and or computation examines and verifies the machine learning prediction. So you need experiments to verify the ML prediction, and so the feedback of the new experiment and computational result increases the database size, because either I am successful or I have failed. So either way the descriptor as well as the targeted properties get added to the database, and the consequence of that, of course, that the descriptor, the targeted properties, and whether they have been successfully achieved or not, that all gets added to the database, and therefore with every iteration the database size increases dynamically. And so algorithms of machine learning are trained again. So now the algorithms of machine learning keep on getting trained. So this is how you mimic a person acquiring experience. So today I have certain degree of experience, basically, which means that I know that certain actions will lead to success, certain actions will lead to failure, but then I keep on acquiring the data based on all actions which I take over a period of time, and therefore I get richer and richer in terms of experience, I get richer and richer in terms of data as time passes. So as time passes, your iterations also go on increasing, and therefore the data keeps on accumulating, and the iterations stop once the desired objective or desired goal has been achieved. So that is what you have you see here, like you have a database, and then you start the first cycle, you get a regression model, then you have a selector which gives you the best conditions, and then you have the experiments or computations for verification. This gets added to the database. If the objective is achieved, then you come out of this loop, but then if the objective is not achieved, then again you go back to the loop, and then you start with the regressor. So basically, so this is the adaptive design approach, where the database gets richer and richer, and the accuracy of prediction also gets better. So I talked about weather prediction. So the data on weather or models pertaining to weather become richer and richer with every passing day, and the richness of this data enables more accurate predictions. So we come to what we call as black box models and white box models. So we have black box models are accurate. They correlate the control parameters, namely descriptors, with the outcomes, namely the targeted properties or targeted material behavior. And these black box models are accurate because they are based on reality, that is they relate real descriptor data with real material performance data. On the other hand, we have white box models which are easy to explain because they are based on physics, laws of physics. They are able to correlate descriptors with the targeted properties in a definite manner, in a definite expression, right. But then they are less accurate because there are many assumptions which have been made. There are many things which are neglected because you want to keep the model simple. So what you are essentially doing is correlating maybe a relatively more ideal situation. So correlating the descriptors with the material properties in a more ideal situation compared to reality. So that is how black box models become more accurate, because they correlate real descriptor data with real property data, whereas white box models are easy to explain from the viewpoint of physics of the problem, or physics of the relationship between the descriptor and the desired properties. So black box learning models are like artificial neural network and so on. So they are machine learning models, deep learning models and so on. White box models that can learn from a set of rules from the training data, that is rule based learning. So you have certain rules which are well defined, and then these white box models can learn from the set of rules. And if you combine the two, as I said, you can have the speed of the you can have speed as well as accuracy. So white box models are used to analyze successful results generated from black box models. So black box models find, because of their accuracy, right, they find successful results, and then these white box models are explain these successful results as to why the success has been obtained, or maybe they can extract some laws, they can extract some correlations, definite correlations between the two, explain the functionality between the descriptor and the targeted property. All reliable materials data from both successful and failed experiments are useful in the progress of developing novel materials, because that is what enriches the database, right. Both success and failure enriches the database, and to determine boundaries between success and failure. So that is what it means. Machine learning in materials discovery greatly enhances the success rate and considerably improves the understanding of complex behaviors of materials as well. So you have black box models and white box models taken together, which make material discovery faster, right. Material discovery is much faster and success rate improves. So you are able to achieve the properties which you had targeted with a much greater probability, right. The probability of being successful gets enhanced very significantly using these models, black box models combined with white box models. So when you take a black box model, you have something that you have prediction which is likely to be successful, and white box model will do the explanation. So what will machine learning do? Machine learning, which is essentially a black box model. So machine learning does many things. It integrates heterogeneous material data So, material data that has typical characteristics of heterogeneity on account of multiple sources will get integrated. When compiled into open accessible databases, the materials data finds applications in materials discovery, material selection, failure analysis and life prediction. So, all these things become possible because these are the performance metrics of the material, these are targeted properties of the material, basically the life prediction or the number of cycles to failure and or something like that, or mechanisms of failure and so on. So, you have a database correlating the material properties, processing conditions, structure of the material, chemical composition with the mechanisms of failure, the life under certain service conditions and so on. Material data is analyzed to establish relations between materials, processes, microstructure, properties and performance. Okay, so, to establish a PSPP relations. So, we are not always trying to develop a new material. So, even among the existing materials, what we establish is based on the data again, which essentially means experience. When what experience when digitalized becomes a lot of data. So, the big data. So, this data can be analyzed to establish the entire processing route to convert the one material or to enhance the properties of that particular material. Let us say I take iron, I want to enhance its corrosion resistance, I want to enhance its creep resistance, I want to enhance its strength under room temperature conditions, I want to enhance its fatigue life, right. So, now I take material data of different materials when combined with iron and see as to what kind of microstructures are needed to achieve all these properties, what kind of processing conditions will give me those material properties, right, or what processing conditions will give me those microstructures which in turn will ensure the kind of performance I am looking for. And so, this material data will when analyzed can give us the processing route as to how the material should be processed. So, for a steel mill, for example, for a steel mill you want to make a particular grade of steel, let us say you want to make a particular grade of steel, what should be the chemical composition, what should be the melting temperature, what should be the casting parameters, what should be the rolling parameters, what should be the heat treatment parameters. So, all these things will be decided when you correlate the when you do when you use a machine learning model to correlate the descriptors with the targeted properties or targeted material behavior. So, this is something which you can do very easily using machine learning. The challenge lies in the materials data sparseness. So, the major problem is the materials data is sparse, it is not the amount of data pertaining to material that is available or reliable data that is available is extremely small in quantity, it is very sparse. Online learning and dynamic learning is another thing which the machine learning can ensure. So, online machine learning applies the learning model incrementally, and as I told you that body of data keeps on growing. So, the training of the machine learning model becomes more and more sound, it becomes sounder and much richer, and the accuracy also goes on improving. So, once you have made a machine learning model, due to dynamic learning the predictions become increasingly accurate. So, online learning dynamically takes the online data to improve computation or the experimental result, and the adaptive design approach uses dynamic learning so that the size of a studied database grows continuously until the goal is achieved, and domain knowledge representation and utilization is also achieved by machine learning. So, it is not that if you use machine learning the importance of domain knowledge diminishes, it is not. Actually machine learning will use the domain knowledge it will represent the domain knowledge in a particular format or in a particular structure and utilize it to correlate the descriptors with the final outcome or targeted properties or deviation from targeted properties as well. So, we have domain knowledge, that is knowledge of material science and engineering, which is the fundamentals which we have learned so far in the entire course. So, that continues to remain applicable and is still in the core. So, material informatics is about transforming materials data into information, into academic knowledge and industrial application. So, basically we are trying to digitalize the core domain knowledge, okay, and then transform it into industrial applications. So, this is how we develop materials, applications of material informatics for material selection, matching with the product design. So, material selection consistent with the product design and the functional performance of the product, modeling and simulation for property and failure prediction, matching materials and processes to make the to manufacture the product, matching with the in-service performance, efficiency of materials. So, basically web-based materials informatics can be applied for so many aspects of materials. So, material solution, so right from material selection or material manufacture to its recycling, at every step you use materials informatics. So, I will show you a brief demonstration of the parameter selection for deep drawing of circular cups. We know that in sheet metal forming you draw a cup using a deep drawing process. So, the sheet, a flat sheet of certain diameter and certain thickness is the raw material, and since we are drawing circular cups, so cylindrical cups, right circular cylinder is the final outcome, we use a circular blank or circular piece of sheet metal of a certain thickness, and we manufacture this part using what is called as a deep drawing process. So, now the parameters here are the blank holding force, the mechanical properties of the material, especially the plastic strain ratio, the degree of anisotropy of the material, that is normal anisotropy of the material, the planar anisotropy of the material. So, basically these two anisotropy parameters play a big role in this. The strain hardening exponent, rate sensitivity index. So, these are some of the parameters, mechanical behavior parameters which influence the deep drawing process. And then you have lubrication, the blank holding force, the velocity of forming, the temperature. So, all these playing a role affecting whether the process will be successful or not. Plus another parameter is of draw ratio, which is how ambitious your draw is. For example, if you are trying to draw too deep a cup, so if you, in a deep drawn part, how deep is deep? So, if you are drawing an excessively deep cup, then the chances of failure are that much higher. So, now the question is, for a given part, for a given cup, I use a blank of a particular size. Now, can I directly draw that blank into the final size of the cup I want in one stage, or I need multiple stages, or do I have to do it incrementally? So, what I do is I take the so called draw ratio, meaning the diameter of the blank, that is the sheet metal raw material, to the diameter of the cup. So, this is called as a draw ratio, right. So, that draw ratio is something which I need to understand. Now, if the draw ratio is too much, I might have to do it in multiple stages, meaning I need to draw an intermediate size of cup, right, and then I might have to arrive at the final size of the cup in a number of stages. So, I will have to draw a number of intermediate cup sizes, so that the limiting draw ratio, meaning the maximum draw ratio that can be achieved in a single stage, is not violated. So, this particular tool which was developed as a neural network software. Basically, it's an interactive tool which is very simple, but then what it tells you is that you give a certain set of material parameters, it will tell you whether it can be drawn in a single stage or not. Then it will try to change the material parameters what could possibly lead to success, and then tell you that look, this material is not suitable, but these are the parameters which are suitable, right. Or in spite of several iterations, if it is unable to find material properties which can possibly enable you drawing in a single stage, it will tell you that this part cannot be drawn in a single stage. So what the code does is that it changes the material properties within the range, of course. So for example, you take steel as a material, it will change the properties of the yield strength, of the value of N, the value of strain coefficient K, then the thickness. So within a certain defined window, within a certain defined limit, and then if it is unable to find optimum set of parameters which will lead to manufacture of the part in a single draw, it will tell you that sorry, it can't be done in a single stage. So let us see how it goes. So we have this window here. So we have so first we load the data. So we have number 2. Okay, so we give the name of the file to be loaded, and so the file is called as circular Okay, so this presently I do not have the file here, so it will get loaded, and then material specifications will be obtained when you click 9. So similarly, you can do this the same thing for the parameter selection for deep drawn rectangular parts as well, and then one can demonstrate to you how the neural network is able to correlate the descriptors. Descriptors are the material properties, the forming parameters which are described to you, and the outcome is the deep drawn part with thickness variation, right. So you have a sheet of a constant thickness earlier all over, but then the deep drawing process creates a variation in variations in thickness. So that is something which needs to be incorporated, right. So that is the targeted property. So depth of the depth of draw and the kind of uniformity of thickness that you can obtain in the product. So if you cannot obtain a successful product, meaning if you cannot obtain uniform thickness of the specified quality, then you cannot draw the part in a single stage. If it is possible to do it, then yes, you can do it, but then so now the software also tells you what should be the processing parameters. Supposing you are applying too much of blank holding force, it will tell you that look, the blank holder force needs to be reduced. So there are a number of changes the software suggests based on the iterative run, and it will tell you what should be the material properties, what should be the processing parameters, what should be the lubrication, and so the speed of drawing has now not been built into this, but then these 3 aspects have been taken care of. Another example is about crystal structure prediction, where you want to discover a stable compound. So you have a chemical composition as the input, and you want to find out the crystal structure which will be stable. So you have you can predict the energy of formation of all possible cell structures. So you take a chemical composition and you can predict the energies that is needed to form different structures. Let us say 14 Bravais lattices is something you try to construct through that particular chemical composition. So, through the set of atoms which you have as a part of the chemical composition. So, now you predict the energy of formation for all these cell structures and pick the one with the lowest energy. So, that is obviously the one that is going to that is most likely to form. And then you have predictive models trained on density function theory data to reduce the computational time. So, this will enable you to predict the energy of formation of all possible cell structures, right, and then you pick the one which is of the lowest energy. So, this is the analytical tool to achieve this objective. Then forward models could predict the formation energy without any structural input about 6 orders of magnitude faster than DFT with no loss of accuracy relative to the experiment. And then you have virtual combinatorial chemistry by scanning most of the almost the entire unexplored ternary space of compounds or the form to identify compounds that are predicted to be stable. That is okay here. So, basically what this describes to you is that you would scan the domain of stable ternary compound. So, XYZ which will give you a stable ternary compound, and then you need to select the ABC. So, these 3 elements which will constitute that compound from 83 technological relevant elements, and XYZ may be obtained using an enumeration procedure taking statistically most common compositions of inorganic crystal structure database and basic charge balance conditions. So, you have here ABC to be selected from 83 technological relevant elements. We need not get into these technical jargons at this point, because many of these like DFT and are beyond the scope of this course. So, we need not get into details of that, but basically what we are trying to understand is that you conduct a scan of the entire unexplored ternary. You basically scan the a number of compounds having this kind of structure, okay, and identify those compounds which are predicted to be stable, and then a total of approximately so many ternary compositions may get scanned to get predictions of formation energy in a matter of minutes to identify about. So, you scan so many and identify 4500 ternary compositions as predictions for new stable compound. So, what it means is that you have a large body of possible ternary compositions, not all of them are necessarily stable. So, you have AX, BY, CZ as the formula for that particular compound, and you have a crystal structure database. You have identified possible crystal structures, and then you scan the database of these crystal structures and the formula for this, and identify about 4500 possible candidates for a new stable compound, and of these 9 were systematically selected for full DFT structure test, and 8 of them were explicitly confirmed to be stable, and this was possible due to so called inverse model. So, inverse model will go in the opposite direction as we have seen in the previous examples. So, you have an inverse model, maybe we will see in subsequent slides as well. So, we have data driven microstructural optimization as another application of materials informatics. So, what we are trying to optimize is the magnetoelastic iron gallium alloy, which is called as galphenol. So, we are trying to optimize the microstructure of this particular magnetoelastic galphenol alloy for enhanced elastic, plastic and magnetostrictic properties. So, what is magnetostriction? When a magnetic field is applied to this alloy, the boundaries between the magnetic domains shift and rotate, and this leads to a change in its dimension. So, magnetostriction would mean that the domains shift and rotate, and this leads to a change in the dimension of the alloy. So, these applications include microscale sensors, actuators and energy harvesting devices. So, you can use this property of magnetostriction, but then you need to optimize the microstructure for the kind of, let us say, actuation you might want, or to the extent of energy harvesting that you might want, or the parameters you might want to sense, say displacement or whatever. So, desirable properties are low Young's modulus, high magnetostrictive strain and high yield strength, because if you have high magnetostrictive strain, then only it will be able to measure the parameter as a function as a sensor. High yield strength is important because it should be durable and handleable, as well as it should be able to take the mechanical loads that might come onto it if it is going to measure mechanical quantities. Again, low Young's modulus, because it should deflect in an elastic manner. So, it is important that the Young's modulus should be low, so that it should be able to deflect under even small amount of load. So, forward models compute these properties for a given microstructure. So, for a given microstructure, these properties can be computed based on the so properties can be predicted by microstructure. You correlate the microstructural features with the kinds of properties, Young's modulus, magnetostrictive strain and yield strength. So, these are the properties which you need, and you have microstructural features to be correlated. Inverse models get microstructures from the desired properties. That is what we were talking about even in the previous case. So, you start with the performance metrics in an inverse model. You want desired properties, you want to have certain Young's modulus based on the extent of elastic deflection that is expected, the extent of magnetostrictive strain that is expected. So, you would take these properties and then construct the microstructure. You would work out the microstructure that would give you these properties. So, then these are inverse models which will get microstructure for the desired properties, and these are challenging because usually there is no uniqueness. So, when you take a microstructure, a number of microstructures can give you the similar set of properties. So, properties might be unique. Let us say I want Young's modulus less than so much, or magnetostrictive strain to be more than so much, yield strength to be more than that much. So, these are unique definitions, but the microstructures which will satisfy these definitions can be just too many. So, that is the reason why the inverse models become challenging, because the microstructure space is just too large to be scanned by these the microstructures, sorry, the number of microstructures which can possibly give these desired properties is very large. So, that makes it challenging. For forward models, the challenge is to scan the entire microstructure space, because microstructure space which will again give these properties being very high. There is no one-to-one correlation between the two. So, maybe 100 different microstructures may be able to give the desired properties. So, you will have to scan a large microstructure space to generate the forward model. The same is a problem with the reverse model. Large microstructure space again is a problem in case of inverse model, because the same set of properties can be generated by a large number of microstructures. So, here is an example of getting a microstructure to give desired property. So, that is we will appreciate numerically the complexity of an inverse model. So, microstructure is for instance represented by an orientation distribution function. Again, you do not try to figure out what it is, with 76 independent nodes leading to 76 dimensional inverse problem, each value representing positive volume density of a crystal orientation. Again, forget this. Basically, you can understand that there are about 76 parameters, okay, so 76 attributes which describe the microstructure, right. Now, you have two possible values for each dimension or each attribute describing the microstructure, basically low and high, right. And so the grain size can be high and low, inclusion content, inclusion size high and low, different sizes of different kinds of inclusions. So there are 50 types of inclusions, each one with a value of high and low. So basically you have therefore 76 different parameters or features quantifying or describing a microstructure, and then each one has got two attributes. So you have 2 to the power 76 combinations that will have to be examined. And so if you examine, if it takes 1 microsecond to compute a property with forward models, it will take about 2 into 10 to the power 9 years to scan the entire space. So the complexity is because of high dimensionality of microstructure space. That is why I said that a large number of microstructures can give you the same property, and that is what it means. So there is a large dimensionality of the microstructure space and multi-objective design requirements and non-uniqueness of solutions. So basically this is what adds to the complexity. So you need random data generation, feature selection and classification algorithms. So you would classify the microstructures into certain manageable numbers so that there is significant data reduction that takes place, right. And then the key step is to prune each search space as much as possible by a search path refinement, and the search space reduction identifying promising regions within the range of each ODF dimension so as to try to reach the optimal solution faster. So basically you search the space reduction or identify the promising microstructures and then try to reach the optimal solution. So basically it involves a large amount of classification of these microstructures, reduction in the microstructure space to reach the final condition. And again, you will not be able to get one single microstructure, you will get a bunch of microstructures which could possibly work out. For example, in the previous case we had something like 8 microstructures which were finally or which 8 of them were explicitly confirmed to be stable. So it is not just a model answer using a model answer giving you just one value, it is there are 8 possible solutions to the same thing. So that is the reason why microstructural getting a microstructure to give desired properties is a complicated problem. So so let us appreciate the role of material science in design and manufacturing. So design and manufacturing are the macroscopic domains, material science is a microscopic domain, and the material informatics therefore bridges this gap, the significant gap between material science and macroscopic design and manufacturing, right. So we have a big difference in the length scales. Material science operates at a very small length scale, very small time scales also, whereas manufacturing operates at a much larger length scales and time scales. Design and manufacturing is largely concerned with predictions of macro scale properties, effective properties and performance of the engineered component and devices. Material science and engineering is focused on fundamental understanding of the physical phenomena occurring in the materials at multiple lengths and time scales. Multiple lengths and time scales responsible for delivering these properties and performance characteristics. So basically, material science is about the physics or fundamental understanding of the physical phenomena which leads to the properties and performance characteristics, whereas design and manufacturing is largely concerned with the outcomes. Basically it is concerned with the final performance, the microstructure which will give that performance, the mechanical properties that will give that performance. So it is concerned mostly with that, which are macro scale in nature. So potential economic benefits therefore would accrue seamless communication from materials knowledge. So, if we can bridge this gap of length scales, small, that is small scale to a large length scale, then there are potential economic benefits that will be realized. And so, this can be done through the PSPP linkage, that is what we had been discussing. So, it is a structure, property and a performance linkage that denotes natural interface for communications between material science, design and manufacturing. So, we have the challenge is in formulating a framework for these linkages, because there is a lack of rigorous statistical approach for quantifying the hierarchical structure of the material, spanning over a multitude of length scales from atomic to macro scale. So, we were able to measure different quantities, different attributes at different length scales, but then the bridging of these gaps is something that remains to be done. So, that is what we had seen in the previous slide also, right in the beginning of our discussion. So, this is the challenge of going from atomistic scale to the manufacturing and subsequent performance related scales. So, in all this, therefore, for our understanding, the role of material informatics is that while material advances will contribute to manufacturing advances and new products, because everything is dynamic, there are going to be tools, more and more tools coming in for generating material data. There are going to be new materials which are going to be generated. So, material advancements will take place and they will contribute to manufacturing advances, they will generate new products. Materials informatics will become the materials handbook of modern times, because the materials informatics handbook can grow to infinite size, it can grow to an infinite dimension, and using computational power you can extract whatever information you want from this particular handbook to satisfy your requirements or to fulfill your purpose. And then you have a hierarchical nature of materials informatics. You have data driven identification of the statistical measures of internal structure of the material and the use in establishment of the high value, robust and reliable property, structure and performance. So, basically you want property, structure, performance linkages expressed as low computational cost reduced order models. So, what we are trying to do is you will have hierarchical materials informatics, where you have data driven identification of statistical measures. So, you will have data driven identification of the descriptors and the and you will be able to explain the effect of the descriptors on the final properties through a robust PSP linkage. So, the robustness of the PSP linkage would mean that even when the descriptor values vary, the final outcome should generally be consistent. So, the few examples of PSP linkages involves the relation between complex porous structure of transport layers in polymer electrolyte fuel cells to the effective diffusivity. So, you have in a fuel cell you have a polymer electrolyte fuel cell having transport layers, right. So, these transport layers have a porous structure, and the complex porous structure has to be related to the resulting diffusivity. So, this is the property, structure, performance linkage. Relate the two phase microstructures in a steel inclusion material system to the effective plastic properties. So, you have two phase microstructures. So, now you have steel and inclusions. So, now basically you are trying to relate the effect of inclusions, the inclusion morphology, inclusion distribution of inclusions, inclusion size, the mean free distance between the between two inclusions. So basically there are a number of parameters characterizing steel with inclusions in place, and how damaging they are, or how they influence the plastic properties. So again this is done through PSP linkages. Now these linkages would be a black box linkage as well, right. Similarly, complex porous structure would not be through a fluid mechanics type of an approach, but it would be through a black box type of an approach, like machine learning type of methods. The extraction of reusable process structure linkages from computational simulations of microstructure evaluation of ternary silver, copper, aluminum alloys using phase field models. So again you have reusable process structure linkage. So you have process structure and property basically. So you have manufacturing process generating a structure and the corresponding property. So you have one can extract from the data, the process structure linkages based on the evolution of the microstructures of this ternary alloy, and this is possible using what is called as phase field models. So you have these phase field models as a part of materials informatics, which will facilitate the extraction of reusable process structure linkages. Predicting local thermoelastic stress and strain fields in multi-phase composites. So you have thermoelastic stress. So thermoelasticity is basically a property of the material where the material responds to a change in temperature, right, with a change in shape. So this so if you heat the material, the shape will change. If you cool the material, the previous shape is retrieved. So that is why it is called as thermoelasticity. So if you cool the material, the shape you started with will get retrieved. So this is slightly different from what we do in, let's say you have a shape that is made at low temperature. Let us say you make a particular shape at low temperature and then you heat it, it will come back to the shape of the raw material. That is what we mean by thermoelasticity. So to summarize, material in informatics is about discovery of new materials and prediction of their behavior under various conditions. Materials informatics is about obtaining a material or a processing route that satisfies a number of performance requirements through the process, structure, property and performance linkages. Materials informatics is about analyzing the large body of reliable, high quality, heterogeneous, multi-source data. So the nature of data is high quality, heterogeneous, multi-source data to extract rules about material behavior, processing conditions, crystal structure, microstructural predictions, properties, etc. It is about a hybrid approach using black box models and white box models together to enhance understanding of new materials as well as speeding up the selection of materials. So with this I think we have some background about material informatics. I would urge you to generally not get bogged down by the jargons. You can I mean this whole lecture is about familiarizing you with what is material informatics, what it facilitates. Basically our handicap is as far as the processing of data that is available. So digitalization of experience that one gets, and continuous growth of the body of data that is going to be available in future, and continuous growth of the tools and processes which will be available to process that data is something which brings material informatics into limelight, and so that is how the potential of materials informatics can be used for generation of new materials for new products. So I think you remember the power of material informatics rather than getting lost in the different tools and techniques that are involved in material informatics. It's a very big field, and it cannot be covered in 1 or 2 lectures, but these 2 lectures are meant to just make you familiar with the subject. It does not give you any expertise, but it gives you a fair idea about what it entails, whether you should get into it or not. So basically, what kind of orientation or what kind of education you would need in future to get into this is indicated by this. So this lecture is mostly indicative in nature about what kind of education you would need to really do materials informatics, and what is the kind of power of material informatics from a user's perspective. Thank you.